In this video, we will determine the currents in separate branches in a simple circuit. The circuit has a 5 ohm resistor in series with a 6 volt battery, and then there's a parallel combination of a 12 ohm and an 8 ohm resistor. Those are also in series with the battery, and it's always good to make a sketch of the problem. You'll be seeing that shortly. We want to use two methods to solve this problem. Just to illustrate, the Kirchhoff's law method does work. So first, I'll simplify the parallel combination, simplify the series arrangement, calculate the currents, work backwards through the drawings to find all three currents. And then secondly, I'll use Kirchhoff's law method to solve three equations with three unknowns, the three unknown currents. So first, taking a look at what we have for our circuit here. If we draw this out, and I'll show you a little bit more of this, but the situation we have is first our 6 volt battery, series with a 5 ohm resistor. There's going to be a current I1 running through the battery, running through the branch of the circuit as I've shown. And then the 12 ohm and the 8 ohm are in parallel with each other. They will have different currents. There are different resistance values. We're going to have a larger current where the resistance is smaller. But I2 on the top, I3 going through the 8 ohm resistor. So my method here is to simplify this circuit. The 12 and the 8 are in a simple parallel combination. So 1 over R parallel equals 1 over 12 plus 1 over 8. Use a calculator and find the value of 1 over P. This is not the parallel resistance. Instead, we have to invert both sides, and the parallel resistance is 4.8 ohms. That's as it should be. It should be smaller than the smallest resistance in the parallel combination. So we have that. And then I redraw the circuit. Taking out the parallel combination, putting in the equivalent resistance, 4.8 ohms. The 5 and the 4.8 are in series. I can add those together. Now I have a simple circuit where I can use V equals IR to calculate the current I1. So that's the next line in my solution here. We know for this circuit, the potential difference around the circuit is 6 volts. That equals the current in the circuit times the resistance of the circuit. We're using a perfect battery here, no resistance inside the battery. So dividing, and you should pause the video and do your own calculations. Make sure you're in agreement with the numbers here. If you ever find something wrong in my videos, please post a comment. I find 0.6122 amps for the current in this circuit. Now, to find the currents for the parallel resistors, I'm going to determine the potential difference across the parallel combination. So I need the potential at point A. The negative terminal of the battery is at 0 volts. I'm going to define that to be 0 volts, so the positive is at 6 volts. To find the voltage at A, we need to find how much voltage drop there is across the 5 ohm resistor. We start at 6 volts. There's an IR calculated drop across the 5 ohm resistance. So that's the purpose of the calculation you see here. We know current I1 multiplied by the 5 ohms. That gives a potential drop here, and we end up at 2.939 volts. That's the potential at point A. Now we can use V equals IR for both of the parallel resistors. V is 2.939 volts across the 12 ohm resistor. So I2 becomes 0.2449 amps. For I3, again, a parallel combination, the potential difference across each member of the parallel circuit is the same. So we're using the same potential difference. So across the 8 ohm resistor now, 2.939 volts, I3 times 8 ohms. And I find that the current is 0.3674, as it should be. It is higher than I2. And how could I check to see if these numbers are consistent, I1, I2, and I3? Well, the current I1 comes to point A and then divides into, or separates into I2 and I3. So the sum, I2 and I3, should equal I1. So if I do that calculation using the numbers that are here, we do find 0.6123 amps. There is some rounding in the numbers I have here. 0.6123 is essentially the same as 0.6122. It's just rounding difference. So we've satisfied that condition. So we can solve this circuit, this simple circuit, using parallel and series combinations, and we come up with a result that we can try to reproduce another way. So here is the second method, using Kirchhoff's laws now. So the same circuit, there are three unknown currents, I1, I2, and I3. So I need to solve using three equations. One of those equations is the one I've just mentioned, I1 equals I2 plus I3. The current that comes to this junction separates into I2 and I3. Junctions do not create current or destroy current. So the current that comes here has to match, I1 has to match I2 plus I3. For the other equations, I'm going to use some loops around the circuit, Kirchhoff's loop rule. And if I start at some place, say start here, I'll put a little X here, then there will be a potential gain of 6 volts going across the battery. There's going to be a potential drop. Now notice that I have these arrows, and I have plus and minus on the resistors, where in this method, where current comes into a resistor, that's the positive side of the resistor. Where current comes out of the resistor, that's the negative side. And I've labeled that also for the I2 and I3 cases. I2 comes into the 12 ohms here, that's the plus side of the resistor, and same for the 8 ohms. So I'm going to select some loops here. There are three possible loops. I'm going to take the outermost one right now. So I go up 6. I have an IR drop of 5 times I1 here. That's R times I, but it's a voltage drop across this resistor. And now I choose to go on the top path here. So minus 12 I2. Why are the minus signs on these terms? Because it's a voltage drop. It's a potential drop. When we go through a resistor in the direction that I've labeled the arrows for the current, we have a minus sign in front of the terms. And then we come back to this point, and the negative point of the battery is at 0 volts. So we come back to the starting point here, and we have no net change in the potential. We go up 6 volts, and we go down twice for the potential drops across these two resistors. We have to end up with no net change for the voltage. For equation 3, I'm going to go through kind of this middle loop. So I start off the same, up 6 volts, minus 5 I1, again a minus sign. As we go through this 8 ohm resistor in the direction of the current, we're going from the positive side of this resistor to the negative side. That's a potential drop, represented by the minus sign. So there's my third equation. I now have 3 equations and 3 unknowns. We go to our techniques of math, and I'm going to eliminate I1 in both of these equations by using this equation 1 to replace I1 with I2 plus I3. So I've done that for both cases here. Minus 5 now will have to be distributed on these symbols I2 and I3. Same thing over here. When we do that and gather like terms, we have a minus 5I2, we have a minus 12I2, so I have a minus 17I2, and then minus 5I3. Again, important, this minus 5 has to be distributed, not just the 5, but the minus sign also. So I have minus 5I3. Over here, when I distribute minus 5, I'm going to have minus 5I2, I have a minus 5I3, and a minus 8I3, so minus 13I3. Now I'm going to try to eliminate here, and I'm going to add 2 equations together. We can always add equations, but before I add, I'm going to multiply A by minus 5, and I'm going to multiply B by plus 17. If you look at the I2 coefficients, minus 17 here and minus 5 here, I want to eliminate I2, so I need opposite signs for the coefficients when I add the equations. That will be accomplished by multiplying by a negative number on A. And then I need the numerical size of the coefficients to be the same size. So I'm going to multiply 17 by 5 here. I'm going to multiply 5 by 17 here. So let's write out the two equations. So minus 5 times this is minus 30 plus 85. Minus 5 times minus 5 gives a plus 25 coefficient on I3. For the B equation, 6 times 17 is the 102. Minus 5 and 17 multiplied give minus 85. And minus 13 and plus 17 minus 221 I3. I can add these two equations. You can always add equations. When I do that, the I2 term drops out. It adds to 0. Plus 85 and minus 85. So it adds to 0 there. The net of the numbers is 72, and the net of the coefficients on I3 is minus 196. So I3 is 0.3673. Again, you should pause and check this calculation in your calculator. Make sure I haven't made an error. So now let's use B and calculate the value of I2. Well, here's my B equation. We know the value of I3, so we'll substitute that in and calculate I2. I come up with I2 of 0.2450 amps. And now use equation 1. We can slide my paper up here just a little bit. Use equation 1 and 0.2450 plus 0.3673, and I get 0.6123 amps. I've kept a few extra digits. Typically I only keep 3 digits in problems, but just to minimize round-off error, I kept those, and these results agree with the easier method. The easier method using the parallel and series arrangement, but again, 0.6123 amps for I1. My first method, 0.6123, and the other numbers are close as well. So you should review parallel and series simplifications of circuit, review Kirchhoff's laws, and I have another video coming up on Kirchhoff's laws that's more complicated. If you want to see the list of my physics and astronomy tutorial videos, example problems, and short lectures, you can go to these websites, totally free, and you'll see lists of videos, a little title, how many minutes long they are, and a description of the contents. Hope that you keep practicing your physics and astronomy calculations and ask your instructor questions.